Great. So yeah, I'm Daniel Nichols, and I'll be presenting our paper on resource utilization aware job scheduling to mitigate performance variability. So this work was done in collaboration with Aniruddha Maratte, Kathleen Shoga, and Todd Gamblin at Lawrence Livermore National Laboratory, and with myself and Abhinav Patele at the University of Maryland College Park. So in this paper, we decided, or we look at the problem of performance variation on high performance computing systems. So this is when a job or a single application with the same input run on the same hardware can experience significant variability within its run times when run at different times. So just for example, here we show two different applications, SW4 Lite and Pennant, run on a HPC system over the course of almost 2 months. And we show along the y-axis here their performance relative to the minimum recorded runtime for each application. And you can see there's a fairly decent spread in relative performance over these 2 months, and even sometimes up to an 8x relative performance for each of these applications running the same exact thing. So this is a pretty common problem on HPC systems. And some of the causes of this and why it happens is one, system noise from the operating system or anything else running on that compute node at the same time. It can come from software bugs or concurrency issues. It can also come from hardware performance degradation. So when different nodes go down, or if the file system goes down, that can cause slowdowns that might not exist in different runs. But largely, and the primary source of performance variation is shared resource contention. So this is multiple applications using the network or the file system at the same time, which will cause that to slow down, and then in turn cause any of those applications using it to slow down. So this is what we decided to look at in this paper, this problem of shared resource contention. And so some common approaches people have taken to mitigating the variability from shared resource contention is one, looking at how messages are sent on the network. So you can change the route which they're sent on the network to avoid areas of congestion. You can add more bandwidth, albeit this is not a practical solution, as if you already have a system built, it's not very cost effective or even possible to add more bandwidth. Or you can look at how jobs are placed on the system via the system scheduler. A very simple example of this is if you had two applications that you knew were going to extensively use the network, you could not run them at the same time or run them very far apart on the network. There's a whole load of different approaches you could take to solve that problem. So again, this last one is what we decided to do in this paper, to look at the problem of performance variation from shared resource contention. And so in order to solve this problem, we introduced the RUSH framework, which is the Resource Utilization Aware Scheduler for HPC framework. And we designed this framework around two key insights that we had based on current literature, which is that we can use machine learning to predict future variation on a system. So given the current state of a system and a job description, we can predict with relatively good accuracy whether that job is going to experience variability or not. And then if we know that variation is going to occur ahead of time, our other insight is that we can modify our scheduling algorithm to more efficiently schedule jobs such that we can reduce variation with that knowledge ahead of time. So with these two insights, we split up RUSH into sort of two main components that aligns with the two insights. The first of these is a module for predicting variation. So here we use system data and job information, and we train a model to predict variability. And then we use that prediction within a new scheduling algorithm to produce more efficient job to resource mappings on the system. So this is the overview of the RUSH pipeline, and I'll first dive into this, the first part, the variability prediction module. So at a very high level, what this is we want to take into a model, we want to take information about the current state of the system, the relative health of the network, of the file system, and such. And we also want to take information about a job. And then given those two pieces of information, we want to predict whether that job run on the current system state will experience variability or not. So here we pose that as this binary classification problem of a 1 if it will experience variation or a 0 otherwise. So to clarify here, we define variability as if a job's runtime is more than 1.5 standard deviations away from its average runtime determined experimentally. You can define this in other ways that are also meaningful, but this works for this paper, and this is what we use for the rest of the talk here. So given this high-level model, given this high-level training task, we want to design a model which can train to make that prediction. So first we need to collect data, which will enable us to train that model. So to do this, we run 7 different proxy applications. So these are smaller applications which mimic the computational workload of larger scientific applications. So most of these are smaller versions of US Department of Energy applications that we run. And we take each 7 of these applications and we ran them 3 times a day from August 2020 to February 2021 on the quartz system at Lawrence Livermore National Laboratory. And for every time we ran one of the applications, we recorded its performance via the wall time from start to finish. And we recorded IO and network counter information via the Lightweight Distributed Metric Service, or LDMS. So with these counters, we aggregated the counters over the 5 minutes from before the job started. And then we also collected performance metrics from several different network benchmarks. These were just small MPI jobs that we ran before the start of a job. And these are there to just gauge the relative network health at the time when a job is about to start. So given this data set with lots of different runs recorded over a long time, we set out to train several different models, and we selected some very common but well-used machine learning models listed here as AdaBoost, Decision Forest, Extra Trees, and K-nearest neighbors. And we trained each of these using stratified k-fold cross-validation, and we recorded the F1 score for each model. And this is the F1 score on the task of predicting if a run had variability or not. It's important here that we use stratified cross-validation and the F1 score because this is a highly imbalanced data set, as not as many runs experience variability as those that don't. And so after this training, we then select the model with the highest F1 score, which you can see on the plot here down at the bottom. Along the bottom, you can see each of the models that we trained, and the height of the bars here is the F1 score that we obtained after training. And you can quickly see that AdaBoost got up to 0.96 F1 score on this training task, and it was the best that we observed. And you can also see an important distinction here that the blue bars show the F1 score when we train on system counters from the entire system, and the orange bars show when we only use system counters from the node that a job is run on. So this is a pretty important thing that we found here, is that we only need system counters from the nodes that we run a job on. And this is important because it allows us to collect the counters quicker during runtime, so we can make scheduling decisions with lower latency. So now that we have these trained models, we then perform feature selection using recursive feature elimination. And here we narrow down to the 20 best features. We chose 20 here because we experimentally determined that that was how many features we could go down to while still getting the same F1 scores. And just as an example, these were the top 5 features from our training with the send rates, receive rates, the number of send packets discarded, and the MPI routine times from our network benchmarks. And then we do this feature selection for the same reason as I just mentioned, in that we want a very low latency feature collection time when we're making these predictions in the scheduler. We want to be able to collect this data very fast. So now that we have this trained model exported that can predict variability, we want to modify our scheduling algorithm to make use of that fact. So here I've displayed a pretty traditional batch scheduling algorithm for HPC. So this is a more generalized version of FCFS plus easy scheduling, where you're given a queue of jobs and you want to match them to resources in some sort of priority order. So given your queue, the first thing you would do is sort that queue of jobs according to some policy. This can be first come, first serve, which is very common, or shortest job first, or something else comparable. And once you've sorted it, then you go ahead and run jobs that can be immediately started on the system in the order of the queue. And you reserve jobs that cannot be currently run, and you reserve them at the earliest time possible on some system resources. And so after you've done that, then you look at all the rest of the jobs in the queue and you determine which ones can be backfilled. So this just looks for small gaps in the schedule where you can fill in short or small jobs without delaying any of the currently reserved jobs. So this is the basic overview of FCFS plus easy. And in Rush, we pretty much leave this algorithm intact. And we look at this start function here, which takes care of launching a job on the actual resources when it's ready to run. So the Rush version of start, we add a conditional check before a job is launched, where we run our machine learning model on the current system counters and a job, and we predict if that job will experience variation or not. And if the model says yes, it is going to experience variability, then we go ahead and put it right at the top of the queue where it was before. And if it doesn't, then we just launch it as normal. And this is the core of what Rush adds to the scheduling algorithm using its machine learning model, with the small caveat that we add a hard threshold on the number of times a job can be skipped just to prevent job starvation. So this is the entirety of the Rush framework and how it works from the machine learning module to the scheduler. And we implement each of these pieces separately, the first part in Python using scikit-learn for the machine learning portion. And then we implement the scheduler in Flux, which is an open source HPC scheduling framework. And it was very important to us that we were actually able to implement this and run it because we needed access to live system counters in the scheduling algorithm. So then we took this implementation and we ran it. We ran several experiments within a 512 node allocation on the Quartz system at Lawrence Livermore National Laboratory. So within this allocation, we ran several different job workloads, each which was about 190 jobs and had roughly a 1 hour make span. And for each of these applications, we ran FCFS plus easy on the workload, and then we ran Rush on the workload, and we ran both of those 5 times to get average metrics. And the metrics we recorded was the make span of the scheduler, the average wait time of the jobs, and the number of jobs that experienced variation. So the first of these experiments, here are the results, where we ran all 7 of the proxy applications I previously mentioned. You can see them along the bottom of this plot here, where we see the height of the bars shows the average number of jobs that experienced variation across the iterations of the experiment. And we can see in black, FCFS plus easy, and in orange, the Rush scheduler. And we see that in pretty much in all of these, that the number of jobs that experience variation on average goes down. For some of these, an extreme amount or a significant amount. And we also wanted to look at the run times to see what the spread of variation looked like within each application. So within the same experiment, we show for each of the applications here, the spread of run times for those applications, where again, black shows FCFS plus easy and orange shows Rush. And we can see here that there's a reduction in the maximum runtime when using Rush for almost all of the applications. And this is important because it allows users to give more accurate runtime caps in their job submission script to the scheduler. So this is a pretty important result from Rush. But we also see that it reduces the total range of runtimes. That's the height of the boxes here. Meaning Rush has effectively reduced the amount of variation in its scheduling. So we also wanted to test the generalizability of Rush. So to do that, we trained our machine learning model on only 4 of the applications, or data from only 4 of them. And then we ran the scheduler experiments again using that limited machine learning model. And then we see that 2 of the applications that were excluded from the data set, we again see, similar to before, that we've reduced the number of jobs on average that experience variation, still pretty significantly in this case. And we also see for the spread of runtimes, here for FCFS in black and Rush in this teal green color, we again see that we've reduced the maximum runtime for each application, and that we've reduced the spread of runtimes, which is the height of the bars here. So even when it hasn't seen the data before, Rush is still able to effectively reduce variation in the jobs it sees. So we can thus conclude that Rush generalizes to applications it's never seen before. And finally, we wanted to look at the make span of Rush. which is essentially just the time from the first job, when that starts, to the end of the last job. So this shows the throughput of the scheduler. So this plot here shows for all the 5 experiments that we ran in the paper, what the total make span was, the time from start to finish, for FCFS in black and Rush in green, with the y-axis showing the total time here. And we see that in all 5 experiments, Rush reduced the time and was thus able to run the same amount of work as FCFS plus Easy in a shorter amount of time. And so finally, in conclusion, after those results, we've shown that a methodology for collecting meaningful historical performance data on an HPC system, and then we've shown how to use that data to train machine learning models to predict variation in applications on the system. And then we've shown how to then use that prediction to schedule jobs more effectively and prevent performance variation. And with this entire Rush pipeline, we then implement it and show that in practice, it's able to reduce the maximum runtime of some applications by up to 5.8%, and also bring the average number of runs that experienced variation down from 17 to 4 in some instances. And that is the conclusion of the talk. Thank you for listening.